Hi, I am Minjeong Kim from Seoul National University of Korea, and let me introduce my study about business operation management applied to electric scooter recharging industry. I'll talk about strategic bundling approaches that could be useful for gig economy operation. The content will start from introduction of my study and flow to mathematical models and brief numerical example and end with conclusions. Recently, dockless scooter sharing service is booming, and it is expected to grow until 2030 as the solution for first mile and last mile transportation. One of the biggest scooter company is Lime, which had started its service in Korea since last year. Lime's electric scooter service is also outstanding when it comes to sustainability. Firstly, the scooter is charged with 100% renewable energy, helping many cities to realize transportation system fully offered by renewable energy, including Paris. Also, parts of scooters are repaired, repurposed, and recycled, leading to better landfill diversion. Also, it replaces car trips, which eventually leads to reduction of pollution and emissions. Therefore, suggestions for business management that helps Lime's service to last is helpful for cleaner environment. The interesting point of this Lime is that they charge their scooters by gig economy. This gig economy is a free market system where organizations and independent workers engage in temporary arrangements via smartphone platform. These gig workers, who are self-regulated, contingent, and individual stakeholders regardless of company's profit, are called juicers in Lime. They are in charge of collecting, recharging, and redeploying Lime scooters and get paid per scooter they've collected by the price shown in the chart. So this is how it works. When time is 9 o'clock when scooter service ends, Lime Company decides each scooter's collection price from $5 to $10, depending on the proximity with other scooters and easiness to approach. Then juicers who intends to participate for collection appears having chargers at home with limited capacity. Each juicers are allowed to make one max reservation, and the later reservation maker has to choose another one if duplicated. Then collection goes on until any juicer finishes its collection. He or she is paid by the price of the scooter, and capacity is filled. Juicer again make reservation among scooters which are not reserved yet, and same happens when other juicers finish their reservation. So as time goes by, juicers finish their collection because of many reasons. First, they filled their capacity. Second, they have no scooters valuable enough to collect in boundary. Lastly, they accomplished their target amount. They recharge their scooters at home at night. So there have left 4 scooters here, and as you see in the chart, cost for recharging has significant percentage. It is critical for Lime to reduce uncollected scooters because of the cost. So my idea is to use complementary and supplementary properties of scooters and provide choice alternatives to collect scooters as bundles to increase collection rate. If bundle A and bundle B with increased price are given, you can see that collection rate increases compared to before. Bundle A is about complementary items which of distance between scooters are near enough, and bundle B is about supplementary items of which distance between scooters are far so that incentives are needed to be attractive for juicer. It is also better for juicers since the value of scooters to juicers gets bigger when it is served as bundles, lowering uncertainty coming from competition and increasing profit, making this bundling system attractive for a juicer. as collection rate will differ by configuration of bundles. The objective of this study is to find the best bundling strategy to maximize scooter collection rate, so I propose 3 different strategies which gives optimized bundle configuration using hierarchical clustering and set packing models. Each strategy provides optimized bundle configuration, and its efficiency will be compared by using simulation of juicers collecting scooters. It'll be checking the collection rate, company's cost change, and juicers' profit. It'll also be compared with Prestage vehicle routing model of optimized collection rate, which will be explained right after. Firstly, this is a Prestage model under ideal situation that Lime has authority to decide juicer's activity. It is for calculating the maximum collection rate under given input data. It is similar to capacitated multi-diploid models with constraint added explaining juicer's characteristic. It'll only be used for small datasets. Next is the first bundling strategy using hierarchical clustering to limit bundle size. Distance of each scooters are calculated and agglomeratively clustered with complete linkage method. Results here show that results may differ by how I set up the max distance. Here you can see there's a predefined radius of circles clustering each scooters with bundle size 100 and bundle size 40. Next bundling strategy idea is to find the best bundle configuration among candidate bundles which are created with bundle generator. When the value of bundle is determined by price and standard spatial deviation of the included scooters, this set packing model right here finds the best bundle configuration, maximizing the sum of the value of winning bundles. There's a constraint that each scooter has to be included in only one winning bundle. Lastly, this model is same from the previous one, from that it is using set packing model among candidate bundles, but the objective function is different. It tries to consider the relation between bundles location and juicers. When incentives are allowed to be provided for bundles which values are lower than predetermined standard, each juicer's probability to collect the bundle can be computed by exponential probability distribution. There's a trade-off such that if more incentive given to that bundle, the probability of bundle being collected grows up. This model finds the bundle configuration while increasing the probability of bundle being collected, while lowering the incentives. To compare how efficient the found bundles were, each bundles created by different strategies are put into simulation. Juicer's collection rule is that it collects the most valuable scooter which gives him or her the best profit per distance. Partial collections are allowed for bundle items. Lastly, when juicer's capacity is over beta %, they only collect scooters which value is over alpha, otherwise go back home. There are 3 collection termination codes, which first is out of capacity, and second is when there is no scooter valuable more than alpha, and the last one is that when there are no scooter left to collect. The simulation results give the root of each juicers and how much they earn, then the information of the cost of the company. For a brief numerical experiment, in as-is system when there are no bundles, 19 out of 27 were collected with juicers having lot of spare capacities. However, with bundles provided, you can see that collection rate goes up and juicers also earns a lot of profit, which is good to both. For the first box with bundles, scooters in one bundle are collected by both juicers, which means bundle is not effective. However, the second and third one, you can see that one bundle is collected by one juicer, which means it is effective. So I'm currently working on more numerical experiments for meaningful results and sensitivity analysis on parameters for each strategies. This study is expected to give cons for both Lime and juicers from that it could lower the cost of recharging by increasing collection rate and providing control abilities of juicers. Juicer can also lower the uncertainty coming from competition and increase their profit and profit per distance, helping them to plan their route. This is end of my presentation. Thank you.